In this lecture, we are going to see some useful remarks. These remarks are useful in the sense that they give more insight of the continuous and discrete random vectors and continuous and discrete random variables. So the first remark, remark 3.2, is basically talking about discrete random vector and discrete random variables. So in theorem 3.6, what we have seen is that if xy is a discrete random vector, if xy as a vector is a discrete random vector, then each components are discrete random variables. Natural question is to ask is that if each components are the discrete random vector variable, is the vector is a continuous discrete random vector or not? And to the answer to this one is yes. Why yes? Suppose x and y are discrete random variables. Okay, so it has some support Sx and Sy. Also Sx and Sy both are at most countable. So now if I take the Cartesian product of Sx and Sy, which is S is also at most countable. Okay, because we have already pointed out that Cartesian product of at most countable sets are Cartesian product of at most countable sets is countable. Okay, at most countable, again at most countable. So that basically means that S is at most countable. Now you can check easily that probability that xy belongs to S is equals to 1. Why this is true? This is true because xy belongs to S, which is nothing but probability that x equals to x, y equals to y. You have to take the sum over this probability. The sum has to be taken over the set S. Because S is the Cartesian product, this sum can be written into two parts. One is over Sx, another is over Sy. Then the inside sum will be probability x equals to x using the theorem of total probability. And then this sum is equals to 1 because x is a discrete random vector. Okay, so that means the probability that xy in the Cartesian product of the support of individual random variables is 1. Now consider the set T. What is the set T? T is basically collection of those points for which the probability that x equals to x, y equals to y is strictly greater than 0. Clearly, T is a subset of S. Why? Because if there exists a point in T that cannot be outside S, because the probability in S is 1, so probability outside S is 0. So that means if there is any point in T has to be in the point in S. So T is a subset of S. Now T is a subset of S. So that now S being an at most countable set, T is also an at most countable set. So and also that probability xy belongs to T is equals to 1. Why this is true? Again, this is true because if this is not true, that means this probability is strictly less than 1. That means outside T there are some points where you have the probability strictly greater than 0, which cannot be possible because of the definition of the set T. So now what we got? We got that T is the at most countable set. T is an at most countable set for which the probability x equals to x, y equals to y is strictly greater than 0, and probability xy belongs to T equals to 1. So that means xy is a discrete random vector. And so that discussion shows that xy is a discrete random variable if and only if x and y are discrete random variables. Okay, xy as a vector is a discrete random vector if and only if x and y are discrete random variables. They are individually discrete random variables. Okay, clear? So that is for the discrete random variable. Now natural question comes with the continuous random variable. So natural things comes into the mind. Is that true for the continuous random variable? That means if xy is a continuous random variable, does this imply and implied by x and y are individually continuous random variables? Obviously, one side we know that if xy as a vector is a continuous random vector, that implies that x and y individually are continuous random variables. Now we need to answer the other side, where if xy are continuous random variables, does this imply xy as a vector is a continuous random vector or not? So to answer this question, so what we are going to do is that we are going to give one example where this thing is not true. So that means we are basically going to show that in general x and y are individually continuous random variable does not imply that x, y as a vector is a continuous random vector. But for giving this example, we need to first discuss the remark 3.3. So remark 3.3 is basically a straightforward extension of the fact that if you have a random variable x, continuous random variable x with density function small f, if I try to find out what is the probability that x belongs to B, I can find out it by taking the integration of the density function over the set B. Obviously, I am assuming here that B is a set for which the integration is a meaningful one. Okay, clear? So this can be easily extended for the multi-dimension. So if xy is a continuous random variable, if xy is a continuous random variable, continuous random vector, if I try to find out what is the probability that xy belongs to A, that I can find out by taking the double integration of the joint density function of xy over the set A. Okay, so if I try to find out if xy is a continuous random continuous random vector, and if I try to find out what is the probability that xy belongs to A, that I can find out as the double integration of the joint density function of xy over the set A. Obviously, again I am assuming that A is a subset of R square such that this integration is a meaningful integration. Okay, so it is a straightforward generalization of this thing for the multi-dimension. This is not only true for the 2-dimension, you can even again extend it for more than 2-dimension also. Okay, now let us come back to the example where we are going to show that x, y individually continuous does not imply that x, y as a vector is continuous. So suppose so the example is a simple one. It starts like this: take any random variable, continuous random variable x, and you take y equals to x. So x is a continuous random variable. As x and y are same, that means y is also a continuous random variable. We are going to show that the random vector xy, basically both the components are same, is not a continuous random vector. That is basically we are going to show. Okay, before going into that, notice that probability that x equals to y has to be equals to 1, because that way we have defined y. Okay, so probability x equals to y has to be equals to 1. Now, if possible, assume that xy is a continuous random vector. So if xy is a continuous random vector, it has a joint PDF. So assume that the joint PDF is small f. Now if I try to find out what is the probability that x equals to y using the previous remark, this is nothing but the integration of the joint density function over the set x equals to y. Okay, clear? So probability that if xy is joint density, xy are continuous random variables, so it has a joint density function, and in this case the probability that x equals to y can be found out taking the double integration of the joint density function over the set x equals to y. And you know that x equals to y is basically a straight line in R square, and that straight line has area 0. That means because the double integration is the volume under the curve, that means this integration has to be equal to 0. Yes? So that means that if xy are continuous random vectors, then probability that x equals to y has to be 0. But in this case, what we got? We got that probability x equals to y is exactly equals to 1. So that is a contradiction, and that shows that xy in this case is not a continuous random vector. Okay, so this remark shows that for continuous random variable, each component are continuous random for x, if xy is continuous random vector, this implies that each components are continuous random variables, but each components are continuous random variable does not imply xy is a continuous random vector. Okay, fine, clear? So now let us go to the next remark, which is again a very useful remark in the sense that it gives you lot of insight. The remark starts with the convert part of theorem 3.6 and 3.9. So in theorem 3.6 and 3.9, what we have seen is that if I know the joint PDF or joint PMF, I can find out the marginal PDF or marginal PMF respectively. Okay, so if I have a if I have a continuous random vector xy, if I know its joint PDF, I can find out the marginal PMF of x, marginal PDF of x as well as marginal PDF of y. So how? That is simple, that to take the integration of the joint PDF with respect to y to find out the marginal PMF of x. Marginal PDF of x. Okay, clear? So now, natural question is that if the reverse true, that means given the marginal, can I construct the joint? Given the joint, I can construct the marginal. Now the question is that given the marginal, can I construct the joint? And the answer to this one is no, we cannot. Again, we will basically disprove this one giving one example, and the example is basically example 3.5. So what is the example? Example start like this. You take two density function f and g. Okay, two probability density function f and g, and you assume that capital F is the cumulative density function, cumulative distribution function corresponding to small f, and capital G is the PDF corresponding to small g. Okay, you take alpha, any value between -1 to +1. -1 and +1 are excluded. Now what I am going to do is that I define a new function. This function is a function from R square to R using the small f, small g, capital F, capital G, and alpha like this. Okay. Now my point is that this small h is a joint probability density function of two-dimensional random vector. How can I show? This can be shown by showing that h is always greater than equals to 0, and if I take the integration of h over the R square, then the value of the integration will be 1. And this one is fairly simple. This is given here. Just take it, and that shows that h is a joint density function of a two-dimensional random vector. Assume that random vector is xy. Okay, right? So h is a joint density function of a two-dimensional random vector, and assume that random vector is xy. So if I have a joint density function, I can able to find out the marginal PDF. So let us first try to find out the marginal PDF. So the marginal PDF of x you can easily find out taking the integration of the joint PDF h with respect to the variable y, and it turns out to be fx. Similarly, if you try to find out the marginal PDF of y, you will find out it turns out to be g. So what we get? We get that this is a joint PDF. We get this is a joint PDF of two-dimensional random variable, and if I try to find out the marginal PDF, they are nothing but f and g respectively. Okay. Now you see that this joint actually going to depend on alpha. Alpha can take any value between -1 to +1, and for any value between -1 to +1, I have different density function, joint density function. But the marginal does not depend on alpha. So what does this mean? This means that I have infinite number of joint density functions by changing the value of alpha. For each of such density functions, the marginals remain same. Clear? So that means that though I can find out the marginals given the joint, but given the marginals, I cannot find out the joint. Okay? Because in this case, which alpha value is actually the alpha value, that I do not know. That means given the marginals, I cannot find out what is the joint. Okay, fine. I hope the example is okay. Again check that whether the example is okay or not. If not, you can ask me in the doubt clearing session. Okay. So as I already pointed out in the last example that given the marginal, I cannot find out the joint in general. But if I have some extra condition, that can be possible. Okay, and one of such extra condition is basically the independent random variables, which we are going to discuss in the next lecture. Thank you for listening.